All right, in this video we're going to run through some of the problems on the worksheet for section 6.3, and I'll do another one with some examples from 6.4. This is just to so you have in a fixed place some examples. These are more or less the same examples we did in class, but I thought it might be useful for you to have it as in a place where you could stop it and pause it and back it up. So remember, the idea was we have a few rules of exponents that we want to use all the time, and the base doesn't matter here, so I'll just use sort of 2s and 3s generically. But the important rules were things like this, that when you multiply two powers of the same base, the exponents add. Notice the base doesn't change. It's the same, whatever the base is, it'll stay the same. And then when you have an exponent raised to a power, so a power to a power, the exponents get multiplied. So those are the two base rules. A side effect of the first rule is that if we ever had a division problem to the A over 2 to the B, then those powers should subtract. And if you think about it, that's really just another variation on the first one. To see that, think about what it would look like if you took what I just wrote down and you multiplied both sides by 2 to the B. Right? It's really just an example of the other rule. And then a side effect of that is that if you had just 1 over 2 to the B, remembering that 1 is like 2 to the 0 power, then this is 2 to the minus B. So in other words, when you have a power in the denominator, as we do here, then that's the same thing as having the negative of that power without the fraction. And so that's basically it in a nutshell. Remember, there's nothing special about 2. You could have a base of 3 or a base of 5 or whatever, but whatever the base is, this is how the exponents should behave. So for example, in the first problem, we're multiplying two powers of 2, and so obviously that's an example of our first rule, which means we still have a power of 2 and we add the exponents. The x plus 3 is the exponent of the first one, and 2x minus 1 is the exponent of the second one, and if I add those two things together, I get 3x plus 2 is the sum of the exponents. And so that's the answer to that question. There's nothing else to it. In letter B, there's a little bit going on here. The most important thing is that we're not going to really be able to do much unless every expression in here is an exponential expression with the same base. And so right away, I'm going to want to change that 4 to be 2 squared. And notice I put the 2 squared in parentheses to emphasize that if I were evaluating this, the 2 squared gets done first, giving me 4, and then that gets raised to the x power. So that really is the equivalent thing, but I have to introduce parentheses to make sure that is bounded correctly. And now I have to use both of the rules that I have above. On the left, in both cases here I have a power to a power, and so I'm going to first resolve that. This is an exponent to an exponent, so I multiply this exponent by this exponent, and you have to make sure that you multiply the entire exponent, x plus 3, times 3. So when you multiply x plus 3, all of that times 3, you get 3x plus 9. And the second one is simpler. It's just 2 to the 2 to the x, and so that's 2 to the 2x. So the powers just multiply. At that point, I have a power of 2 times a power of 2, and so the first rule says those powers should add. So if I add the exponents, 3x plus 9 and 2x, I get 5x plus 9. And so that's my completely resolved exponential expression. The one below that is very similar. Again, starting off with the fact that the denominator, the 9 in the denominator is really 3 squared. So that's the same thing. And now both in the numerator and denominator, I'm using the rule about power to a power. In the numerator, this is 3 to the 2x plus 2. It's multiplying the two powers, but again, I have to make sure I multiply all of the power x plus 1 times 2. And in the denominator, I have 3 to the 2x. And so this is sort of a curious one because with the rule for a fraction of powers, we subtract. And if you subtract the two powers, the 2x plus 2 in the top minus the 2x in the bottom just leaves you with 2 squared. And so this is, sorry, 3 squared. So this is a little bit odd that no matter what x you put in here, letter C, this expression of letter C simplifies to just be 9, no matter what. And if you don't believe that, just try it. Take, put like 5 in for x in this thing and see what you get. You'll get 9. You put negative 17 in for x here, you'll get 9. It doesn't matter. So, so that's the idea. Let me just write the first step for the rest of these. And again, the answers to these are posted on the online version. There are 3 pages to the one that's posted online, and the third page has the answers. So you don't need me to tell you that here. But the right first step here, 27 is 3 cubed. And so again, that's how to rewrite the problem so that everything in there is an exponential base 3. And then we can use a combination of our rules to simplify it. 25 is 5 squared, and so this expression (5 to the x over 25) is the same thing as 5 to the x over 5 squared, and so you can see that it looks exactly like one of these problems now. And then the f, of course, is the trickiest one because there's a lot of stuff going on there. 4 is 2 squared, and so I have 2 squared to the x minus 1/2. And this part, this 1/2 here to the x, well, 1/2 to the x, 1/2 is really the same as 2 to the minus 1. That's what this guy tells us. So 1 over 2 to the first is the same as 2 to the minus 1. So instead of 1/2, I could write 2 to the minus 1 to the x, like that. And so I've changed this 4 to be a power of 2. I've changed this 1/2 to be a power of 2. Now I've got just powers of 2 everywhere. And so again, I can use a combination of these 2 rules to simplify that to a single power of 2. Okay, there were some things about domain and range and intercepts. Let me just sketch here what the graph we got. We said this thing goes through 0, 3. It goes through negative 1, 0. Those were my intercepts. And so it got close to, gets close to 4. This, and falls off the table that way. So this exponential graph, like I said, all exponential graphs will have one direction where the graph is falling off the screen and the other direction should be hugging an asymptote. It's pretty easy to tell which one's which just by not only plotting your intercepts, but plotting like the extent of your window. So putting in like x equals 4, so like f of 4 here is whatever that is, like 3 7/8, whatever that is. So if you figure that out, so it's getting close to 4. On the other hand, at this extreme, f of negative 4 is something like negative 28. So it's way, way, way down off the screen. So by just checking the the output for the 2 x's that are the extremes of your picture, you can definitely get a feeling for in which direction you're approaching the asymptote and in which direction it's sailing off the screen. And so if you do a few of these, you'll know it's not a coincidence that your asymptote is basically, you can see it here. You can see that y equals 4 would be your asymptote because the exponential part, this is the part that in one direction goes crazy, gets huge, and in the other direction gets close to 0. So that's what this exponential part does. In one direction it gets huge, and in the other direction it gets close to 0. And so whichever direction is getting close to 0, this function is going to get close to 4. And when this thing gets huge, then this guy gets negative huge. And so that's what we're seeing here, that in this direction we get negative huge, in this direction we get close to 4. And so that means that our range is minus infinity to 4. The boundary of the range, right, these guys are going to match because the asymptote is a boundary to the y-coordinates, right? That's what it means if you look at it. That dashed line I drew is like a barrier that the curve can't get across. And so the range of this function is everything on one side of that fence. And so as soon as I know which side it's on, then I know my range. And so if those 2 answers don't match, then something is very wrong. Okay. But more of the point is going to be doing algebra, and that's going to be solving equations. And this collection of equations from section 6.3 is special in that we can approach these using our laws of exponents, and we can write these so that both sides of the equation are exponentials with the same base. And so let me just give you an example. So this in part A, the right-hand side is just 2 to the fourth. Right? 16 is just 2 times 2 times 2 times 2. And so the one-to-one property of exponentials, the result of a function being one-to-one is that if two outputs of the function match, then you can't, well, that's not the right way to say it. It's impossible to have the same output from two different inputs. That's the better way to say it. So remember the basic exponential function, the basic 2 to the x function, to the x, not that. The basic 2 to the x function looks like this, goes this way and has an asymptote this way. So that's what 2 to the x looks like. It's increasing everywhere, so it's one-to-one. It passes the horizontal line test. The result of that, when a function passes the horizontal line test, that means that it's impossible to get the same y-coordinate from two different x-coordinates. Okay, look at the graph, make sure you believe that. On a graph like this, it's always increasing. It's impossible to have the same y-coordinate from two different x-coordinates. If a graph does have the same y-coordinate from two different x-coordinates, that means it fails the horizontal line test. The only way you could have that would be to have a graph like that. That would be a graph where there's 2 points that have the same y-coordinate from two different x-coordinates. So that's not what's going on here. And so we know that the 2 to the x function can't have the same output from two different inputs. And so therefore, if you see this, this is saying that the output from using x plus 3 matches the output from using 4. So the only conclusion would be that the inputs are the same, that that's not two different inputs. And so what that looks like algebraically is that if we have an equation between exponential expressions of the same base, then the only way that those two things are equal is if their exponents are equal. And of course, that's an easy equation to solve, right? That would be x equals 1. And since that's easy to use, we could check that and see that that's right. So that's the idea. In each of these, again, let me show you how you can write these as powers with the same base. 16 is 2 to the fourth, right? We just said that. And so the left-hand side in part B is really 2 to the fourth to the x plus 1. And the right-hand side is a half, which we said on the other page was the same as 2 to the minus 1. And so there I have expression on both sides that are exponentials of base 2. So with one extra step on the left to make that a single power of 4, so remember we have this rule that says that if we have a power to a power, we can multiply the powers together. So that's the same thing. And now we have power of 2 equals power of 2. And so now I can say that the exponents are equal. So when the bases are equal, when the exponential expressions are equal with the same base, then the exponents have to be equal. Same deal with C. Remember 8 is 2 cubed. So on the left I have 2 cubed times 2 to the x. I know I can resolve that. On the right I have 2 squared to the x. I know I can resolve that. Right? There's two different exponential rules going on, but it's very easy to write the left-hand side is 2 to something and the right-hand side is 2 to the something, and we're off and running. Same deal in letter D. There's really not much different. 9 is 3 squared, and so that would be the same equation, but now everything is written in terms of exponentials with base 3. So anyway, so I hope that helps. That's just the getting the examples that were on the worksheet, and as I said, if you want to try the ones on your own that I didn't finish here or didn't take to the end, try working them all the way to the end, and then look online for this handout from section 6.3 and compare your answers to my answers.